Swayam Prabha. Digital India. Educated India.
Okay, good afternoon. Yeah, so we continue with morning's discussion. So we had in the entire virtual address space, basically we had the page translation table. This essentially we will call it as page table. Okay, the word that is commonly used in the literature is page table, and we at the start of the page table was given by CR3, right? Sorry. So this was a physical address space. There was a page table here inside this, and then the start address of this was given by is stored in CR3. Okay. Now what basically happens is that in the morning discussion we said that we need something like 1024 entries, okay, and each of 4 bytes. Sorry, 1024 entries? No. Two power 20 entries. Sorry. Each of 4 bytes. Okay. So this is something like 2 power 22, which is 4 megabytes of memory will be used for setting up this page table. Okay, right? Because 2 power 20 is 1 megabyte, each 4 bytes, so 2 power 40. So before going further, so that's one big disadvantage, like 4 MB of the memory is just used for, you know, the storing the space translation mechanism. This is one important thing. But before going further on that, please see that the page frames in your physical address space, which I call it as PAS, actually starts at, so since each page is 4096, it starts at 4 KB boundaries, okay, and so on, right. So the page, the starting address of a page will be in a 4 KB boundary. That means the last 12 bits, if we take this as 32 bits, the last 12 bits will always be zeros for the start of a page, because your page frames are 4 KB, it starts with 0, next will be at 4 KB, next will be 8 KB, 12 KB and so on. So that means it is at a 4 KB boundary. That means the start address of every page will have the last 12 bits as 0. These 12 bits I can basically use for other constructive purpose, right, and I will tell you 2 interesting things that we use these page bits for. One thing is there is something called a valid bit. The valid bit says that whatever I have entered, see, if I look at any 32 bits, it will be a random 0 and 1. So any combination of zeros and ones in that 32 bits will make some sense to me, right. So in this 12 bits, one of the bit will be valid bit, which I will set it to 1 if the corresponding page is loaded. I will set it to 0 when the corresponding page is not loaded. So I have 220 pages, 2 power 20 pages, and for each page I have an entry. In that entry, the last 12 bits I will be using for some constructive purpose. One of the purpose would be one of those 12 bits. What is that bit? Prasanna will tell you at 3 o'clock. That bit, essentially, if it is 0, that means that page is not loaded in memory. If that is 1, means that page is loaded in memory. So when I load a page, I will go and make that bit as 1. correct, that valid bit as 1. To start with, all the bits will be 0. I will make that bit as 1, that means that page is loaded. So when I have this 32-bit effective address, right, I take those 20 bits and index into this table. After indexing into this table, I will go and check that valid bit. If that valid bit is 1, then we go ahead. If the valid bit is 0, me means who? The architecture, the hardware, right. It will go, and if the valid bit is 0, then it will raise a page fault, correct, because that page is not actually loaded. Then the page fault handler will start working on it. Are you able to get it? Yes or no? So this is very, very important. So that is something that we need to keep in mind. Okay. So one bit is the valid bit. Another bit, I call it clean bit, but Western world call it dirty bit. Okay. But what do you mean by dirty bit? Okay. So we will go with dirty bit because ultimately somebody else will ask for dirty bit. Okay. So see, why we need this dirty bit? Can anybody tell me why we need this dirty bit? Dirty bit is after I load that page from the disk to the memory, have I gone and changed something in that? If I go and change something there, immediately that dirty bit will become 1. If I do not change anything there, then the dirty bit will be 0. Why do we need this dirty bit? Can you guess? When I want to replace a page, so morning somebody asked, no, what happens, all the pages are full. I go and replace a page. When I replace a page, I mean I am going to overwrite on an existing page, correct? I am going to overwrite on an existing page. When I am overwriting, should I go and copy the original page back and then overwrite, or should I not copy the page and just overwrite, right? So let us go back to that 54, something. Yeah. So I want to replace say P1 by P6, or so because P7, I want to replace P1 by P7. Now if P1 is, maybe P1 was the least recently used, I have only 6 pages, now I have to replace someone. So the interrupt service routine, the page fault handler decides to replace P1. If after loading into the memory, if P1 was changed, right, then I have to copy the entire P1 back here and then load this P7 here. After loading into the memory, if P1 was not changed, it was read but not written into, then I can just overwrite P7. Now taking this 4096 bytes and putting back into the disk is also a very time consuming affair, and there is no need for me to do this, right, there is no need for me to do this if this fellow does not change at all. If P1 did not change at all, why should I copy the same thing back again? If the copy on the virtual address space on the disk and the copy in the main memory are same, I need not go and rewrite it, correct? If the copy in the virtual space in the disk and the virtual memory, the RAM, the physical RAM are different, then I have to go and write back P1 and then write P7. So the moment I go and change something in the page, the hardware goes and makes that dirty bit as 1, so that in case you are going to replace this page, what do? You go and copy this entire page back to the virtual address space and then they copy this and then overwrite on top of it. Okay. If this dirty bit is 0, then you do not do anything, just overwrite, correct. So that is another interesting bit. Of course there are some privilege levels also, that there are some more bits that we can use, and then there will be still a lot more bits available, and these bits can be used to implement page replacement policies. The operating system will judicially use these bits, can use these bits to basically implement certain policies, the replacement policy like least recently used, which page to replace given this. Are you able to follow? Any doubts? So now do you understand how I am exploiting the availability of some redundant bits, the 12 bits for basically doing this valid check and the dirty check, and we get lot of performance enhancements based on this. Is it okay? Is it fine? Any doubts? Now the big challenge that we have is this 4 MB. Should I have 4 MB? Okay, right? Now very few programs will use all 4 GB address space. 4 GB is a huge address space. Your Gmail is only 12 GB, 15 GB now, right? And it takes a lifetime for you to fill it up. Okay. Now this 4 GB is a large address space for many practical use, unless you are going to do some high-ended supercomputing problem, okay, or very high-end VLSI problem or some simulations. For normal usage, even for normal sort of even online web transactions or database, even banking systems or your railway reservation, you will not actually load that entire 4 GB address space with your program, right? So one of the thing is that this 4 MB that I want to basically store for page table, can I do something better? So that's the question. So now that gives us, so not only in Intel, there are many other architectures which follow this today, what we call as multi-level paging. Okay. Now what is multi-level paging? We will just look into it very shortly. It's very simple actually. Okay, in multi-level paging, what we do is the entire 32 bits, right, I make it as 12 bits, 10 bits and 10 bits. Okay. Now CR3 points to the start of one page, start of a page, which I call it as page directory, PD. I call it as, instead of page table, I call page directory. So this page directory will be one page. That means I will have 4096 bytes. That means 1024 4-byte entries. Each of these entries here will point to another page will point to start of other pages, and these pages also have, these are also 4096 bytes, and they will have 1024 4-byte entries. Now each of these entries will point to the actual pages. Okay, so this is called page directory, this is called page, these are all called page tables, okay, and these are the, and they will point to the actual pages, right. So instead of having one level of translation, now I have multiple levels of translation. So what I do, I take these 10 plus 10 plus 12, the first 10 bits I will index into, this fellow, because there are 1024 entries, I have 10 bits, 2 power 10 is 1024, I will index here. This will point to another page table. To this page, let us say it is pointing to this. To this I will take the next 10 bits I am marking in blue here to index into this, because this will also have 1024 entries, right. So I will use this 10 bits to mark onto this 1024 entries. This will point to some page, some start of a page. That page will have 4096 bytes. I will use these 12 bits to index into that, and that will give me the actual physical memory that I need to access. You are getting this? So now instead of having only one translation of 4 MB size, what I am doing, I have one page directory which will have 1024 entries, 4-byte entries. I will use the 10 most significant bit into index into that table, into that directory. That directory, we call each of these entries as PDE, page directory entry. Each of those entries will point to a page table. So I go to the corresponding page table, namely here, and use the next 10 bits, next 10 most significant bit to index into this page table, correct, and that will give me the start address of a page. Okay. To that page I give, that page has 4096 bytes, so I use the 12 bits to index, and this will be my actual location I want to access. So instead of one direct translation I go through 2 levels of translation to basically get the address I want. Is it okay? Are you able to follow? Note that each of the page directory will fit in 4096 bytes, and each of these page tables will also fit in 4096 bytes. So somebody asked me why 4096 bytes in the morning. This is one explanation for 4096 bytes. Okay. So this will also fit. So each of the page table, the page directory, everything will fit in one page itself, right. And so what happens now, instead of one lookup, now I go to 2 lookup. First time I just go and look up one table and then just add the address and take. Now I look up one table, that gives me another table, look up that table, add the address and go and access. But since everything fits into a page, the last 12 bits of everything, for example, for the last 12 bits of this page table, what does this say? What does this entry in the page directory say? It points to the start of a page table. And again, since everything is page aligned, that last 12 bits will be 0. So those 12 bits can be used to find out if there is a page table associated with it, is it present or not. I can tell that. So I can do one check here of whether the corresponding page table is, if nobody in this address is basically accessed, then that page table will not be even fetched up. Okay, right. So then what happens, then even in the page table, again the pages are again 4096 bytes aligned. So so ultimately the 12 bit will be 0, and that could be again used for all the other purpose. Now, so this multi-level paging, what I have created, I have 1024 plus 1, 1025 pages are needed to finish this off. 1025 pages are needed to get these things up, right. In the previous case we had 1024 entries, right, what did we have, 2 power 20 entries divided by, sorry, we had 2 power 22 divided by 2 power 12, we have something like 2 power 10, 1024 page tables we had last time. 1024 pages it will occupy. Now this will occupy, actually in the worst case, this will occupy, in the worst case this will occupy what, 1024 plus 1, 1025 pages, one more page extra. But then please understand that when I see, always the 4 GB will not be full. For all the holes or wherever it is not being used, that corresponding page tables can be thrown off. It is not mandatory for me to have all the 1024 pages here. I certainly need the page directory which will occupy one page, sorry, right. I need to have the page directory, that is always there. Now the respective page tables inside that page directory need not be populated immediately. As and when I need, I want to I will populate, and I don't need, I can throw it off. If there are no programs, so all the programs that are executing falls within these 2 addresses, these 3 addresses, then I will have only 3 page tables for this. The remaining things I will just leave it off as invalid. So, and suppose the program corresponding to this has finished, I can throw that page off and I can use that page for some other purpose. So this means that the size of the page table is directly proportional to the amount of memory you are actually utilizing, correct. If you are not utilizing some amount of memory, then the corresponding page tables corresponding to that address can be thrown off. Are you getting this, right? So the amount of paging I use, the amount of page, number of page tables I use, the size of the memory that is actually reserved for page table crucially depends upon the size of the actual memory being used. So this essentially, this multi-level paging basically gives us a mechanism of a dynamically growing and shrinking page translation mechanism, right? So when there are a lot of pages being used, corresponding page tables and page directories, that corresponding page tables will be loaded. When some pages are finished, I can throw them off. When I want, again I can print. So I have now an on-demand page table, right? Like what we talked in the morning as on-demand paging, now I have an on-demand page table. Is it all fine? So this is the advantage of multi-level paging in contrast to the single level paging. Any doubts? Are you able to follow? Right. So the next thing is that now what has happened? Now I do some amount of segmentation, I get an effective address. After getting the effective address, I first go to the page directory entry. From there I get some entry. With using that, I go and index that and I go to the page table entry. There I get some value. That I take and add the remaining 12 bits and access the page. So there's a lot of memory access. One memory access. Now assuming segmentation, we are not accessing memory. Even before I find where that particular data is there, I am gone. Right? Now that 2 now have become 3 and 4. Right? So it is just increased. Are you able to follow this? So what we do is that we also have an associative memory or a content addressable memory, wherein we just go and store what we call as page translation buffer. In this I go and say this page K is loaded in this memory location, this page frame. So I have a mapping between the actual pages that are loaded in the memory and the corresponding starting address of the page frame. So I have a mapping between the effective address and the physical address. So what I do is I go to this I go to this PTB, page translation, and ask, hey, can you do the translation for me? This fellow says, no, I can't do because I don't have that entry. Then I go and do all these. By the principle of locality of reference and locality of spatial locality and the temporal locality, I know that this page translation buffer as a concept will succeed, correct? The PTB as a concept will succeed because, so this is also called in literature as translation Lookaside buffer. So I could have, what I mean by translation Lookaside buffer, do not go and do the translation, just Lookaside it and throw it off. Come to me, I'll tell you what the translation is. So for many instances this TLB will help because we are having this spatial locality and temporary locality. So what will happen is at many instances this translation Lookaside buffer will give enormous performance boost to the virtual memory system. Okay. So now what we will do in the lab, starting now the lab statement will be given, but then we will also, so it will be an extension of your third assignment, but the point, first assignment, extension of your first assignment, just check if you are remembering that. There are some points that you will do when you do the code, you will understand, and tomorrow morning I will debate on that in great detail. So what is it to enable paging? Till now first is 2, 3 you have not enabled paging. What it means to enable paging? What are the cares that need to be taken when I want to enable paging? So that is one thing that we need to keep in mind. The second thing that we need to also talk is what are these page replacement algorithms, how they are going to come. So several of those background I will try and cover. The difference between a single core and a multi-core is there are two major differences, how these cores are interconnected. There is an interconnection work that is happening. The second thing that we need to be careful about, moving from a single core to the multiple core is that how the memory is being accessed. How they are interconnected is one story. How the memory is going to be accessed is another story. So tomorrow we will do a deep dive on this. How do we set up and what are the things, why 4000, all these why and what we will try and answer in tomorrow morning's class. Any other doubts? Yes.
Does a page translation buffer?
See, so when I give a address of a page, right, instead of going, if I give this 32-bit, instead of going here, then here, then here, after I do one page translation, that data, right, this page is stored at this page frame. So if the second page is stored at this frame, then I need not do the other processing. Correct? So it is something like I give an address to that PTB or translation TLB and ask, hey, is this address already loaded? Is this page loaded? It will not only say yes, but it can also say that where it is loaded. Okay? Right? It will tell you where it is loaded. So that will be given in this translation. So this is very close to your BTB, right? What branch target buffer says, whether the branch is taken or not, and if it is taken, then it will also give you the target address of where it should go. Similarly here, this TLB will tell you where it is loaded and if the page is at all loaded and where it is loaded, which page frame it is loaded. So directly I can go to the page. Okay. TLB you can't see. TLB is invisible to the assembly program. But you can basically see the, I think there are some performance counters which can tell you how many TLB hits are there that we can probably program, but not in your, we are not looking at performance in this course at all, but we may look, I'll give you some pointers about performance counter later. But otherwise we can basically implement this page. So what will you be doing in the assignment is you will set up this entire translation mechanism. And what you do is that this page directory, there will be one thing separate, and you will make CR3 point to the start of the page directory. There will be one page, there will be 1024 entries. Then what you do that, and the pages here, right, you take some 2 pages and you will be mapping, I think Karthik will be explaining you that, right, and then some of the things that you need to take care is that page table, the page containing the page directory, the page containing the page table, these need to be identically mapped. Identically mapped means if I am storing it at say 4097, right, I need that same 4097. If it is not identically mapped, then you go into subtasks. Okay, so the page that I am mapping onto is identically mapped. You are getting this? And if you have any doubts, you can go to my Information Security 2 course. Again, we have done the same thing there. So you could have a feel of how things work there. So all the things that I am teaching are also part of Information Security 2. It's not there in the web, but I think you are given a link in the Moodle, right? Just go and understand that. That will give you a lot more value. Okay?